Alrighty, we are going to be talking about the root test, which is going to be our last test for this unit. And it's going to be very similar to the ratio test, so if you haven't watched the ratio test yet, go ahead and do that before watching this one. Essentially, with the root test, what we're going to do is take the limit as n approaches infinity of the root of the absolute value of my terms. And if that limit is less than 1, then the series that we're trying to find is going to be absolutely convergent. If my limit is greater than 1, or if it is infinity, then my series diverges. And if my limit is 1, then we have to try another test because it will be inconclusive. With the root test is going to be very good if you have an exponent, some sort of exponent with n, just because if I were to rewrite this into exponential form right here, I have the limit as n approaches infinity of the absolute value of the terms, but then I have 1 over n. Because if I have an exponent of n over n is going to cancel out because this is just going to be 1, and then I'm just going to be left with the absolute value of my terms, which is essentially my end goal for these types of problems. So looking at number 7 right here, notice how I have a 2n and I have an n right here. So what I'm going to try and do is try to manipulate this so that I have an n as an exponent. So I have e squared over n, and that's going to be to the nth power. Once I do that, I'm going to do the limit as n approaches infinity of the nth root of the absolute value of my terms here. And let's make sure that I have an n inside. Right here. Well, if I were to convert this into exponential form, I have the limit as n approaches infinity of the absolute value of e squared over n to the n. And then I have 1 over n. Well, the n and the 1 over n, like I said, cancels out. So now I'm just left with e squared over n. And since we don't really have any alternating terms and we're starting at 1 right here, I am going to remove the absolute value bars. So now I have this lovely thing right here. Remember that e squared is just a coefficient. So now this essentially is going to be e squared times 1 over n. And as n approaches infinity, 1 over n will approach 0. So now I have e squared times 0, which is just going to be 0. So this lovely thing right here, if I can make it pretty, will be 0. Since 0 is less than 1, this tells me that my series right here will converge absolutely by the root test. Yay. All right, number 8. Once again, I am going to take the limit as n approaches infinity. And then because I have a 3n right here, I'm going to skip this part and go straight to this right here. I'm going to have the absolute value of negative 3n over 2n plus 1. And this is going to be an exponent of 3n. But then I have 1 over n. The 3n times 1 over n is just going to be 3. So I have this lovely thing right here. Looking at my coefficients, because my degrees are the same, this is going to be negative 3 halves as n approaches infinity. But then I have the third power, so now that's going to be negative 27 over 8. And since I have an absolute value sign, I'm going to change it to 27 over 8, which is greater than 1. Since my limit is greater than 1 right here, this tells me that my series will diverge by the root test. Sad. All right, same thing with number 9. So the limit as n approaches infinity of the absolute value of ln of n over n. And then I have n times 1 over n, which is just going to be 1. So now I have infinity over infinity, which means I'm going to use good old L'Hopital's. And the limit as n approaches infinity of 1 over n is just going to be 0. Which means that since it's less than 1, we know that the series will converge absolutely by the root test. Finally, for number 10, and then we'll do some mixed practice. The limit as n approaches infinity of 2n over n plus 1. Looking at my degree, since they're the same, I'm going to look at my coefficient, which is just going to be 2. And since 2 is greater than 1, this tells me that my series right here will diverge by the root test. Sad. All right, so those are 7, 8, 9, and 10. 11, 12, 13, 14 are going to be very similar. You are going to have to use a little bit of algebraic moves for number 12 right here. Split that up to -1 to the n and -1 to the -1 so that you have an exponent of n. That's fine. This is fine. This is fine. 13 might be a little bit tricky if you don't know inverse tangent, but you should be good there if you know what that is for 13. All right, mixed practice. We are going to determine if the series is absolutely convergent, conditionally convergent, or divergent, and we are going to state our test. All right, now, because we are talking about conditionally convergent, what we are going to do is take the absolute value of our series and see if it converges or diverges. Remember, if my absolute value of the series diverges, this tells me that I potentially might have a divergent series, or I have a series that's going to be convergent, but it's going to be conditionally convergent. All right, so for 15, I'm going to go ahead and take the absolute value of my series, and I'm going to find out if n over n squared plus 1 converges or diverges. And what I'm going to do here is think about what I could use. This isn't going to be geometric because I don't have an exponent term. This right here kind of looks like a p-series, but it kind of looks like a comparison p-series. So let's go ahead and try to do a comparison and see what happens here. So we have n over n squared, which is going to be the same thing as 1 over n. And we know that 1 over n is a divergent harmonic series. So by the comparison test, by the p-series comparison test, the absolute value, and we're going to set all of this right here to be a sub n, the absolute value of a series diverges. Now, because that diverges right there, I'm going to look at my original series using the alternating series test. And the reason why is because I have an alternating series right here, so I only need two things. I need to make sure that my limit approaches 0, which it does. And then I also need to make sure that my terms are decreasing. If my terms are decreasing, then we know that satisfies that condition. And since both of them are both conditions are satisfied, I could say that the series is conditionally convergent. So I'm going to go ahead and look at 1 over n squared plus 1. If I were to plug in 1, that's going to be 1/2. If I were to plug in 2, 4, 5. If I were to plug in 3, 4, 5, and so forth. And you can see that my terms are always decreasing. Since my terms are always decreasing, I know that my conditions are satisfied. Now, this right here isn't going to be the best in terms of my justification. Remember, with my justification, I kind of need to prove that everything is decreasing, meaning that I kind of need to use I gotta find the derivative and see where my derivative is negative. But for the sake of time, just trust me in terms of me saying that the terms are decreasing. So by the alternating series test, we know that my series is convergent. So overall, this tells me that this series right here is conditionally convergent. So that's my final answer. All right, number 18 is another problem where we have -1 to the n plus 1. Since we have an alternating series, I'm going to go ahead and use the absolute value, bars, and I have n is equal to 1 to infinity of n to the n and n factorial. Remember that if I have some sorts of n factorial right here, I'm probably going to be using the ratio test. So I have the limit as n approaches infinity of the next term. And then I'm going to multiply by the reciprocal of my original. So I have this lovely thing right here. All right. Now remember that n factorial, n plus 1 factorial, everything will cancel out except the n plus 1, because remember that n factorial is n minus 1, n minus 2, n minus 3, and n plus factorial is n plus 1, n minus 1, n minus 2, n minus 3, so forth. Everything cancels out except n plus 1. So now I have the limit as n approaches infinity of the absolute value of n plus 1 to the n plus, oops, this should be a 1 right here, since I forgot to include that right there, times 1 over n to the n. Now notice how here we have n plus 1 to the n plus 1, and then we have an n plus 1 right here. So I'm going to use properties of exponents and say that this right here can be simplified to n plus 1 to the nth power. Now both of these right here will be infinity over infinity, and I could use L'Hopital's, but remember that we're talking about in terms of relative growth rate, in terms of the limit as n approaches infinity. Since we're talking about relative growth rate right here, notice how my exponents are the same. I have an n right here and I have an n right here. The only problem is my base is n plus 1 on the top and my base right here is n at the bottom. So because my numerator is a little bit heavier, because it has an n plus 1, this right here will diverge. So this tells me that this right here, if this was a sub n, tells me that the absolute value of my terms diverges. The absolute value of the sum of my terms diverges. Now, because that diverges, I'm going to have to look at the alternating series test to determine if that converges or not. All right, so the limit as n approaches infinity of n to the n and n to n factorial. We kind of saw that. No, we didn't. I was going to say we kind of saw that here. But if I were to think about this right here with n to the n, and n factorial, this right here will approach infinity, just because the exponential right here grows a little bit bigger than the factorial. So this right here tells me that the alternating series test does not apply. So the alternating series test does not apply, which means that I have to use another test. In this case, I'm going to use the nth term test, because usually if the alternating series test doesn't apply, the nth term test will apply, because then we know that the limit will eventually diverge with the -1 to the n plus 1, because this diverges right here, we could say that the series right here diverges by the nth term test. All of that for the nth term test. Crazy. We should have started with that. But obviously, because we had a alternating sign, I would encourage you to probably work with this first before doing the nth term test. Okay, number 19. Once again, as a little reminder, because I don't have an alternating term right here, if I take the absolute value of this is going to be the same thing as my original series. So if my series is convergent, then automatically it's going to be absolutely convergent, just because I don't have a negative term anywhere in terms of my series. We're going to be using the root test. So I have the limit as n approaches infinity of 1 plus n over 2n squared. The n over n will cancel out. All right, so if I take this limit as n approaches infinity, this is going to be 1/2. And then if I were to square that, that's going to be 1/4. And since 1/4 is less than 1, this tells me this right here is absolutely convergent by the root test. Alrighty. That was fun. 17, 20, 21, you're going to have to use absolute value. So make sure that you look at that because some of them might be conditionally convergent. For 22, this is probably going to be the root test since you have an exponent of n. And then 16 kind of looks weird because I have a sign to the 2n and then I have a 1 plus 2n, 2 to the n. So probably the comparison test with the geometric series maybe, since I have 2 to the n right here. But try to compare that with something that works in terms of 16, and then we're good. Now, because we have finished all of our tests right here, it's going to be very important for you guys to know all of the tests that we've learned. So there is a formative that's going to be very helpful for you. And it should say ratio and root test additional practice since this is the last lesson. So do that in preparation for your Unit 2 test. All right. Unit 3, we are going to be talking about the power series and all of that good stuff. That's going to be after the Unit 2 test. So we're going to have fun there too.